video we're going to have a look at the limit as theta goes to 0 of sine theta on theta, which is one of the tutorial problems in Chapter 2 of your calculus notes. It's a very important limit in calculus, very interesting limit. You can't evaluate it by simply substituting in because you get an indeterminate form 0 on 0. So in this problem we're going to use a rather nice geometrical argument to show that this limit in fact exists and equals 1, which is a kind of surprising result. So in our picture we've got a right-angled triangle and we've marked a length across here. The base here is 1 and we have an arc length here to make part of a circle. So this is 1 unit up there and then we extend it up to make our right triangle. And we drop a perpendicular from where this arc meets this hypotenuse. We drop that down to here. And so we have an angle theta, and we've got two lengths marked as 1. They're the radii of the circle, and I've marked the other vertices as you see in the picture. So the first part is we're asked to write down expressions for the arc length, firstly the arc CB, and that's easy because we have a formula that says the arc is just r times theta, where r is the radius of the circle, which is 1, and theta is the angle. So provided theta's in radians, of course, that will be the correct answer. CA, well, to do this one, I look in this triangle and I can see that this length CA over 1 is the sine of the angle. So CA is just sine theta. That's easy. And DB, well, I'm going to be looking in this big triangle now, and I can see that that over 1 will be the tangent of that angle. So I can write down those three expressions very easily. The next part says to consider some areas and compare some areas to try and derive a particular inequality that I'll put up in a second. So just looking at it, looking at the diagram, it's pretty obvious that the area of this triangle is less than or equal to the area of this sector, which in turn is less than the area of the big triangle. And that's what I've written down here. So I'm just going to calculate each of these three areas. So for the triangle OAC, so I need half the base. Now OA we didn't calculate earlier up here, it wasn't asked, but doing that we can see that if I work out the length OA over 1, then I have the cosine of the angle. So that means that OA is cos theta. And the height we did work out, which is AC or CA, and that's sine theta. On the other hand, we can get the area of the sector, and the area of the sector here is again half r squared theta. R is 1, so I get a half theta. And the area of the big triangle, well again that's going to be half the base times the height. So the base is 1, height is BD, which is tan theta. So I get that nice, that collection of inequalities, and all I'm going to do now is just multiply through by 2, and then I have the formula that I was required to get in the tutorial problems. And so that's part B of the problem. For part C, we're now going to try and in fact get the limit not of sine theta on theta, but the other way round. Well, you can see they're going to be connected, so I'm going to try and get theta on sine theta. So I'm going to divide this inequality through by sine theta. Got to be a little bit careful because you're dividing by sine theta, which can be negative, but if my theta is in the range 0 to pi on 2, then all is well because it's positive. So I divide by sine theta, so I get cos theta is less than theta on sine theta. Now, of course, tan, you all know when you see tan theta, that's sine over cos. And so when I divide by sine theta, I'll just get 1 over cos theta. And having it in that form now, we're interested now in what happens. So I should really say here for theta between 0 and pi on 2. I better exclude the 0. So for theta in that range, then this inequality holds. And now I'm interested in what happens as theta goes to 0 from above. So as theta goes to 0 from above, then cos theta goes to cos of 0 is 1, and so both of these terms here end up as 1 in the limit. So by the pinching theorem, So by the pinching theorem, we can say that the limit as theta goes to 0 from above of theta on sine theta is equal to 1. And that finishes off part C. By the way, we could have turned all these terms, we could have inverted all these and reorganised it and simply had the 1 over cos theta there and the cos theta there, and that would have flipped this upside down. And exactly the same argument gives you that the limit of sine theta on theta is 1. So we also know that that's true. For the last part, we want to look at the limit as theta goes to 0 from below of sine theta on theta. And the trick we're going to do here, all I'm going to do with this is I'm going to replace theta with minus theta. So wherever I see theta in this limit, I replace it with minus theta. So that is going to give me then the limit as theta goes then to 0 from above. So rather than going from below, it goes from above because I've changed the sign of theta. This gives me sine of minus theta on minus theta. And remember, sine is an odd function, so I can pull the minus out and they cancel. And so I'm going to get the theta goes to 0 from above of sine theta on theta. But we've already seen, we know what that limit is. That limit is also 1. So we've shown that as theta goes to 0 from above, the limit of sine theta on theta is 1, and as theta goes to 0 from below, we also get 1. So for our conclusion, which I'll put in here, our conclusion is that the limit then as theta goes to 0, either from above or below, we get the same answer. So that limit exists and equals 1. And that's what we were trying to show.